All right, physics party people, here's our video on torque. So it's an introduction to the concept of torque. We'll go more in depth on this stuff later. But torque, take a moment and just look at these memes around here. So this one on the top left, another Greek letter. But it's basically the same as something else in linear motion. Torque and forces, they are back and forth. So it's everything that we have been doing as far as, oh, here's a rotational thing. Now let's just figure out what's the actual thing that we're used to that it is an analogy to, which for torque is forces. The door meme in that top right is kind of a funny one to us teachers. We'll get to that when we're in class, but basically, a door and how we open doors is all about torque. All right. So, what is torque? Well, torque is when we apply a force just to somewhere that's not the center of mass, which, as we've talked about before, a force not at the center of mass makes things rotate. And we just call that torque. That's all it is. It's just called torque, which is given by this lowercase Greek letter tau. Now, when you write this letter, I will write it as just one kind of wiggly line, kind of like you're about to draw a pi, but it's just one. It's kind of like a lowercase t, but with a um, kind of a wiggly, squiggly top kind of a thing. So that's tau, is how we say that, or torque. In our analogies, we've looked at delta theta, or angular displacement, to displacement. We've looked at angular velocity to velocity, angular acceleration to acceleration, rotational inertia to mass, which is basically just inertia. There's another one that we've done that is not on here. L is angular momentum, is analogous to P, linear momentum. Now we're doing one last one, and we do get to bring back the sum of the forces, but instead our analogy is the sum of the torques. It's I know it's not quite as nice of a ring to it, but here we are anyway. So torques and forces, it's basically the same thing. We can apply the equivalent of Newton's second law with sigma tau, as we have with the sum of the forces, sigma f. So torque, now the official definition is a cross product, because radius is a vector and force is a vector. There's this thing called a cross product in vector math, which if you're in pre-calculus or above, you might have heard of that. If you haven't heard of that function, no worries, because here's what you need to know: RF sine theta. RF sine theta. So it's the radius. So from the pivot point to wherever the force is being applied, that's the radius there. So radius, and then the force is whatever the force is that's acting on that location that we decided right there. So the force, and then sine theta, that theta is the angle that's between the radius and the force. It's whatever that angle is, theta between them. Now we like to say perpendicular, or what I might say for this is R perp F, where perp just is perpendicular, and that is kind of familiar to you with with work. We've done FD cosine theta because it's whatever force and displacement are parallel. This is just kind of the opposite to it. Whatever radius and force are perpendicular. So we have a sine theta of the ones between them. But that means that if radius is this way and force is this way with a 90-degree angle between them, that is the maximum torque that we could possibly get, is 90 degrees, because sine of 90 degrees is 1. All right, if we take sine of 90 degrees, we get 1, as opposed to if they were along the same direction, it'd be sine of 0, which is 0. All right, so we have R, radius in meters, we have F, force in newtons, and we have theta is the angle between those two vectors. Moving on, the units of torque. So we've got our unit dog coming back. What units would torque get? Well, in rotational motion, we don't have any special new units. It's just the combination of the units that we have been using. So torque, we'll put it in units of, well, there's a radius, and radius is a distance, so that's in terms of meters. Forces is in terms of newtons, and sine theta, whenever we take the trig function of an angle, it cuts off all units that get associated with it. So there are no units with sine theta. So torque, we just have in units of newtons times meters. Newton meters. Now, this is something that, if you remember back to our energy, right, we can say work is force times displacement times the cosine theta. Well, force is in units of newtons, displacement is in units of meters, and then the cosine strips away the units. So work, but we know that work is in units of joules. Work is in units of joules, but essentially that's us saying that a joule is equivalent to newtons times meters. It's a weird kind of a thing. Work and energy we put in joules. Torques we put in Newton meters. It's one of those weird, just kind of colloquial things that physicists do that we're just kind of used to. That there's not a great explanation necessarily, other than that's just how people do it. So that's the way that people see it and expect it. So torque is in units of Newton meters. All right, so here's some guiding questions. I'm going to suggest you pause the video, read through these questions, and try to answer them using our equation that a torque is a singular torque, an individual torque, and maybe I'll write that down here. An individual torque is equal to, oh, my computer's having some problems. An individual torque, RF sine theta. Take a moment and pause the video and walk through these questions. See if you can come up with answers for them. First one, why do you use wrenches and screwdrivers to turn bolts and screws instead of just your fingers? Well, if it's just your finger, right, if it's like a six-sided bolt or something like that, if you're just using your finger, then you're only at that location. But if you're using a wrench, right, wrenches kind of extend all the way out here. So all of a sudden, we're using this radius as opposed to just this little radius right there. So we're really increasing our torque because we have a much bigger radius on the wrench. Screwdrivers are kind of a similar concept. Why are door handles on the edge of the door furthest from the hinges? Well, here's our door. Let's say our hinges are on the left side. If my door handle's on the right, that gives me a radius to the handle all the way across the door. If my door handle was in the middle, somewhere like that, then my radius is only that far. And we want to maximize our torque, which means we can have more torque for less force if we have a bigger radius. So we want that bigger radius so we don't have to exert the same amount of force. Just try it next time that you're opening a door. Try opening that door in the middle, or try opening that door right next to the hinges. You'll notice a huge difference in the amount of force that you have to exert, because if your radius has gone down, then your force has to go up to exert the same torque that you normally would to open that door. All right. Why do we use a steering wheel instead of just turning the steering column with your hand? Well, in a car, essentially in a car, there's the steering column is just one metal rod that just goes down, and there's gears around the bottom of it. And those gears, when you turn the steering column, the gear turns, and then the gear meets up with another gear here. And that's what kind of pivots the wheels to go back and forth that way or that way, whatever it is. But if we are only using our hands, then the radius that we have is just from here to here. Whereas instead, if we use the whole steering wheel, let's say this is our steering wheel, right? And our steering wheel, it kind of, right, it has the horn in the middle. Most steering wheels are kind of shaped like this with kind of that four part there. Let's maybe say you have one of those fancy steering wheels with the little buttons on the side and whatever. But all of a sudden, our radius now goes from, instead of just being the width of the steering column of that metal rod, now it's the width of, or the radius is the whole radius of the steering wheel. So it's a much bigger radius. So it's a lot easier to turn the car because you can turn the steering column a lot easier. One last one. Why do we have pedals on our bike instead of just spinning a little tiny disc? Well, hopefully you are kind of in the habit of how we're going to answer these questions by now. Here's your bike. All right. And our pedals right here. Let's say that's our little disc right there, but we have pedals that extend outward from there because all of a sudden our radius isn't just that big, our radius is that big. So bigger R, we don't need to exert the same force to, or we don't need to exert as big of a force to get the same torque. If radius is bigger, force is smaller, all those kinds of things. All right, let's take a look at some examples here. We've got a 16.3 centimeter wrench on a bolt being used to turn it. You apply a force of 65 newtons to the end of the wrench perpendicular. What torque are you applying? Well, an individual torque is given by R, F, sine theta. Well, we're told this is perpendicular, so that means sine of theta is sine of 90 degrees. Sine of 90 degrees, which sine of 90 degrees is 1. So that just multiplies away to 1. So all of a sudden our torque is now just equal to R. Well, the wrench is 16.3 centimeters long, so our force would be applied at the end of that. And the force we are applying is 65 newtons. All right, so if we calculate this torque, 0.163 times 65, I get 10.6 Newton meters. Sorry, that was my cat getting fed in the background. 10.6 Newton meters. There's our torque. However, let's say we use the same wrench. Okay, so the same wrench, that tells me same length is that wrench, to tighten a bolt that's harder to reach. So maybe it's under a table or whatever. You can only apply a force of 34 newtons at an angle of 37 degrees away from perpendicular. Oh, notice how I italicize away from perpendicular. So that's me telling you that angle, 37 degrees. All right, well, our torque equation, torque is equal to torque. An individual torque we can solve by setting R, F, sine of theta. All right, well, radius, it's the same length of wrench, so 0.163 meters. The force we can apply is now only 34 newtons. Sine of theta. Well, theta, remember, it's the length, or it's the angle between the radius and the force. So it's not 37. Instead, we have to find what's that complementary angle to it, which would be 53 degrees if we take 90 minus. So we need to do sine of 53 degrees. Okay, so now let's plug this into our calculator. So 0.163 times 34 times the sine of 53 degrees, and I get a torque of 4.43 Newton meters. If my computer stops having a conniption. All right, 4.43 Newton meters. Moving on. To show some similarities here to linear forces, right, an individual force, we can do the mass times whatever the acceleration would be from that individual force, such as force of gravity is mass times the acceleration of gravity, g. Torque is similar. Now it's just the angle gets involved a little bit too. But we can also say if there's multiple torques involved, all we have to do is just add them together. Now, similar to forces, some could be positive, some could be negative. In forces, usually that is up and right. typically. Now, there's exceptions to that, like Atwood machines or inclined planes, things like that. But torques it's just rotation, and usually we'll say counterclockwise is positive because that's what the unit circle does. Balanced forces, oh, and that's a typo over here. This should say balanced forces. My apologies. Balanced forces is an acceleration of 0 meters per second squared, whereas balanced torques is alpha, angular acceleration of 0 radians per second squared, where the positive torques equal the negative torques. Very similar to forces. It's now just for things that are not angularly accelerating as opposed to not linearly accelerating. So this is constant velocity is where that occurs, whereas over here is a constant angular velocity or constant omega. All right. So let's take a look at a couple of these. Mary spins a merry-go-round. Sorry, before we get into this, I didn't emphasize enough this part right here, that the sum of the torques equals I alpha. I alpha, because I, rotational inertia, is basically our rotational equivalent of mass. And then alpha, our angular acceleration, is our rotational equivalent of A, acceleration. So the sum of the torques equals I alpha. So that AP gives you this equation in the form of alpha equals the sum of the torques over I, over the rotational inertia. That's how AP gives you that equation. Now it's similar to AP giving you this one. They give you acceleration is the sum of the forces over mass. So they give it to you in the same exact format as each other. It's just a little bit different than we look at it as far as ease of writing things down goes. Just to know that is what to look for on your equation sheet is alpha equals the sum of the torques divided by I, the rotational inertia. Okay. Mary spins on a merry-go-round on a playground from rest. Ooh, from rest. Okay, omega naught equals 0. Just writing that down before I forget it. 0 radians per second. She takes 1.2 seconds to complete one rotation. Well, one rotation delta theta equals 2 pi. Is one rotation is one circle during a constant angular acceleration. Okay. The merry-go-round. Oh, get it? Because it's merry. Can be modeled as a disk with a mass of 112 kilograms and radius of 3.4 meters. And then the rotational inertia of a disk is given to you right there as the equation. What is the angular acceleration of the merry-go-round? Well, angular acceleration, we're looking for alpha. Now, in this alpha, well, we have omega naught, we have time, and we have delta theta. Okay, so if we want to put these all together, we can use our expression delta theta equals omega naught t plus 1/2 alpha. Sorry, my computer is having a really hard time. Alpha t squared. All right. Now, if we just plug some of this stuff in, 2 pi is our angular acceleration. We start from rest, so that whole term goes away to 0. 1/2, we are looking for alpha. Time was 1.2 seconds. So 1.2 seconds, and we can square that. Well, maybe my pen will let me. Okay. So we get then 2 pi. I'll multiply both sides by 2, divide both sides by 1.2 squared, and I get alpha, angular acceleration, 8.73. Wow, sorry, my pen is having a really hard time. 8.73 radians per second squared. All right. So that is our angular acceleration, 8.73 radians per second squared. of this merry-go-round as it's accelerating. Okay. We're going to try to make the pen work a little bit better this time. All right, moving on. What was Mary's net torque exerted on the disc? Well, torques, we can say that a torque is, right, there's only one torque here, the sum of the torques, because if we're relating torque and angular acceleration, it's just like relating forces and normal acceleration. We use our sum of expression. So the sum of the torques equals I alpha, but the only one was Mary's push torque. So I'll say the torque of push. All right, well, I we're given as 1/2 mr squared. So 1/2, the mass was 112, the radius 3.4 meters, and that gets squared, mr squared. So there's I. Alpha is 8.73 on this disk here that we got from part A, so 8.73 radians per second squared. And that'll give us our torque of push. So we can throw this all in together. 1/2 times 112 times 3.4 squared times 8.73, and we get a torque of 5,651 Newton meters. And there's our torque for Mary on this disc. All right, with how much force did Mary push on the outer edge? And we're assuming no friction on this, which that really does apply to this previous one too. There's no friction to slow that disc down. So force, right, if we have an individual torque, we can say torque is RF sine theta. Now, it should say, and I apologize for not saying this, that Mary pushes perpendicular to that playground, because Mary's a physics student. She knows how to exert the largest torque with the smallest force, and that's with a perpendicular angle with as big of a radius as possible. So we can say that the torque, 5,651 Newton meters, radius at the edge of the disc, because Mary would push at the edge, she's a smart physics student, would be then equal to the force. So 5651 divided by 3.4 meters, we would get that the force would be equal to 1,660, going to 3 sig figs, newtons. So there's our force that Mary pushes with. All right. If there's that problem there, let's keep chugging along. We now have a bike rider uphill when pedaling. She puts all her weight, 65 kilogram rider. She puts all her weight when pedaling on the pedals. The pedals have a radius of 17 centimeters. What is her maximum torque when the pedal is 45 degrees above horizontal? Okay, so there's 45 degrees. And her weight, if that's the pedal, the weight is going straight down. All right. So here's kind of the different, or a slightly stranger interpretation of this, because our angle between these is 135 degrees. Right? We have the 90 degrees that's to that level bit, and then we have the 45 degrees, that's the extra part there. Add that up, 135 degrees. So we can say that the torque exerted by this person pushing down on her pedal, RF sine theta, and the radius of these pedals, 17 centimeters, so 0.17 meters. The force would be the force of gravity on the person, so mg, 650 newtons is mg, and then times the sine of the angle between the radius and the force, so 135 degrees. And we can just plug that in right there. So 0.17 times 650 times the sine of 135, get an answer of torque being 78 Newton meters. Okay, so that's when the pedal is horizontal. Now the question becomes, what about when the pedal is or I'm sorry, that's when the pedal was 45 degrees above the horizontal. Now it's what about when it's horizontal, because the force of gravity is straight down and now our angle is 90 degrees, which means RF sine theta, this sine theta will be sine of 90 degrees, which is 1. So now we can just say the torque is RF, so 0.17 on those same 17 centimeter pedals, times her force. Well, it's still her force of gravity is the maximum force that she can put down. So 650 because it's mg, looking at her 65 kilogram mass there. So that torque, we can get 0.17 times 650, and I get 110.5 Newton meters as that maximum torque when it's horizontal. All right, so there's those. We just have one more example problem for you here real fast, with a couple of different torques. So let's look at adding these torques up together. Calculate the angular acceleration of the wheel shown with these forces. There's also a frictional torque. Ooh, frictional torque. We haven't had one of those yet. Opposing the motion. Wheel has rotational inertia. Oh, so I just give you I right there, so you don't even have to calculate it. All right, well, we're relating angular acceleration and forces, and we have radius and stuff here. So angular acceleration is alpha, and we want to relate that to forces. We're going to have to go through torques. So the sum of the torques equals I alpha. And now we've got to figure out which way does it turn. Well, we don't have to know. We just can say, let's choose one direction to be positive. Now, usually it's counterclockwise is what we choose to be positive. More than welcome to do that. What I'll look at here, though, real fast is, this 35 Newton force is pulling it clockwise. The 25 Newton force is pulling it clockwise as well. And the 15 is the only one going counterclockwise. So I'm thinking there's two clockwise torques. I'm just going to say, let's make clockwise positive for this, just so we can say it's moving in the clockwise direction. All right. Because, and here's the important part of that, frictional torque is opposing the motion. So we have to know which way it's going to know which direction the frictional torque will be. So if it will go clockwise, then that'll tell us that the torque of friction will go counterclockwise, just so we can know to have this as the correct positives and negatives. All right, so we can say, and I'll say the torque of the 35, and then I'll say another positive is the torque of that 25 Newton force. The torque of the 15 Newton force is backwards, and then minus that torque of friction. Okay, so then we can say the RF for each one of these individually. So RF, and actually, I'm just going to break these down into numbers first. So the torque of the 35, well, R is 0.12, and then F is 35 newtons. And then sine theta, well, there's R, there's F, so perpendicular. And actually, we can kind of see that for all of these torques here. There's the radius, there's the force. So all of these torques are perpendicular to the radius that they are on, so we don't have to worry about any of our sine thetas. Okay, so then the 25, we have a radius of 0.24. Oh, so this torque actually is getting twice as, this force is twice as powerful as the other forces because it's twice as far. That one will also help us to ensure that clockwise is positive because it's twice the amount of torque as an equal force on that inside circle. Okay, and then the torque of the 15, well, we're back to the 12 centimeter radius here, 0.12 times our 15 Newton force, and then minus our torque of friction, which I say is 0.4. So 0.4, if I can get my pen to work, 0.4 Newton meters is that frictional torque. All right, so then I alpha, and I'm going to plug in my I because we know Our rotational inertia is 11.5 kilogram meter squared. And then let's solve for this right side of this equation here. So we get this 0.12 times 35 plus 0.24 times 25 minus 0.12 times 15 minus 0.4. And I get 8 over on the right side. That's a nice round number. All right, so then divide both sides by 11.5. And I get my acceleration, my angular acceleration, 0.696 radians per second squared. All right, there's my alpha. Okay, so this problem was designed to show you when we take multiple different torques that some are in the same direction, some are in different directions. We can still treat them exactly like we've done forces. We just have to take into account the radius as well. All right, we won't get into this application in this video, not mathematically. This is our last slide. So just to tell you that this is coming, linear momentum, right? We did P equals mv, and we've already made that analogy into angular momentum of L equals I omega, which the angular equivalent of mass is I, the angular equivalent of velocity is omega. But we'll go into, because we had linear impulse before, force times time. Angular impulse is basically the same, just the rotational equivalent, torque times time. Just to know that that's coming, that's one of our applications of torque. But we'll get to that. We'll have a whole separate bit of learning on how to do those. Just as a precursor toward that, just know that it's coming. All right, so there's our video on torque. If you have any questions, if you run across anything, let me know. Otherwise, that'll do it for this video. Hope you have a great rest of your day, and I'll see you next time.